Okay, I think we'll start the afternoon session here. So pretty much the afternoon session here to close to 3, I guess, or something here. We're going to combine with the PM team, the flex team and the PM team will be combining. Read on the 3 really good speakers here and some really good topics. So to start out with, we're going to hear from Bill Buttlar from the University of Missouri. He will be presenting on the Missouri reflective cracking test sections, which are companion sections to the mineral sections. So please welcome Bill.
And we should be live. Good afternoon, ladies and gentlemen. It's been a while since I've been in the great state of Minnesota. It's just great to be back. Great to see a lot of old friends here and some new faces. And yeah, I've kind of continued my journey from Penn State and Pittsburgh and Pennsylvania to Illinois for 20 years. I keep moving southwest, a little warmer. I'm in Missouri now, been there for 10 years. And really pleased to have continued, though, to work with my friends in the upper Midwest and talk about one of my favorite topics, which is reflective cracking. And so we'll give you an overview of the project, talk about the balanced mix design, performance testing that we're doing, the field sections that we built and that we're monitoring, and then the integration with pretty advanced modeling that we have going on at Mizzou. And so, yeah, reflective cracking, it's a persistent distress. You know, it's interesting as a professor, one of the things you get to do if you stay in the field for a long time is you can have problems that you solve in a month. You have problems that you solve in a year. But then you get to work on these persistent problems, and you might take your whole career to work on them. And so hopefully I'll be at this for a little while. We've made some progress with reflective cracking, but this is it's almost like you set yourself up for failure when you put asphalt on top of a cracked up substrate, whether that's cracked up asphalt, thermal cracked asphalt here, jointed concrete pavements of any sort, jointed and cracked. Maybe you have a modified soil system that develops transverse cracks, and then you put asphalt on top of that. So any of those systems can drive that crack upwards. And in the past, when I first started research in the mid-1990s, there was a proliferation of different fabrics that were being used to provide some kind of a stress absorption or base isolation technique. Some went soft, stretchy, some went stiff. So you had fiberglass and stiffer geogrid type materials. Then you also had softer polypropylene geotextiles. You could also try to get after on concrete pavements that isolated cracks by fracturing the entire slab. So different types of crack and seat, break and seat, rubbleization can be effective, but at a cost. The cost would be you're putting a thicker amount of asphalt, you got to worry about bridge clearances and butting up against shoulders and intersections. And so, you know, getting rid of some of that structure and adding it back on with asphalt, there's certainly a cost there. So you gain the reflective cracking mitigation, but you also gain a lot of cost and other headaches. So we just wondered, nowadays, asphalt isn't what it used to be in the 1990s. We have SMA on the surface. We have, you know, high mod. We have different super paved binders and better aggregates in the mix. And one of the things that I remember hearing from people at the Illinois Tollway, I did a lot of work for them, and they said, you know, when we started using SMAs, we noticed that thermal cracks kind of went away, but reflective cracks sort of went away. We see them, but they don't affect the ride quality very much. They don't spall as fast. And to the traveling public, they're almost invisible. And so this idea of maybe don't try to solve reflective cracking in every solution, but maybe try to mitigate its deduction on overall performance. And so we wanted to test some of these hypotheses on Interstate in Missouri. And we were also using additives, plastics, modern, simple plastic additives in asphalt. We are more of a PPA, polyphosphoric acid modification massacre binder state than we are SBS. You can almost not find SBS polymer in Missouri. So that's a novelty to us, call us crazy. So we wanted to look at like PPA versus SBS versus just recycled polymers, scrap tires, GTR, engineered chrome rubber, and different plastics. in the context of a reflective cracking study. So that's what this project is all about. And so the reflective cracking challenge, and I think there's another speaker that's going to speak to that tomorrow. Eshan, you going to have a second talk about that tomorrow? So I'll just talk a little bit about it, but there's projects obviously going here at Min Road, and then in Missouri, just out on our interstates, and then at the NCAT test track. And there's polymeric overlays, but it could be asphalt over asphalt, asphalt over concrete is what Missouri did. Different climate zones, and then to exchange data. So there's the partners, you'll hear more about it. But as for the Missouri part, the I-155, if you're familiar with Missouri, we have a so-called boot heel. We're one of the states that touches 8 states. I think Tennessee also does that, but so we collect connection to a bunch of states down here with a boot heel. And south of St. Louis, it's a pretty warm climate down here, but the traffic isn't as heavy. So this is a location where, according to the MoDOT designs, you can do a super paved surface or SMA. So they wanted this experiment also to look at dense graded super paved versus SMA. And it was a pretty long section. You got Hayti up here and Caruthersville here, and then the river crossing out of Missouri and into Tennessee. So the dense graded sections are on this page, and you can see there's 6 of them. There was 9 total sections, so there's 3 SMAs on the next page. And this was done at a time when we were ushering in one of the early states to do balanced mix design. And so we were doing selected projects where you had to bid on the project with BMD. And this was right around that time a few years ago. And we used the ideal CT cracking test. And so on the CT index, when we scored mixes that were designed before we had any cracking tests really going, it wasn't too uncommon in our climate to find, a score of 30, 25 on that test. And so MoDOT was going to try to get everybody running the test and then just sort of up the bar. And so they were in the process of going from like 30 to 45 to 80. And then that's on the dense graded mixes, and then eventually a much higher number for the SMAs, as you'll see. So we were kind of experimenting with that, seeing how that would change the mix designs. Turned out that the control section, they were targeting this and ended up meeting the 80. And so we had to kind of flip which one we considered as our control section. But you can see here some of the combination of factors. These are all dense graded. So the factors are a control, which would have like a V graded massacre binder, which would be via PPA modification. The engineered crumb rubber, there you start with a softer PG grade, something like a 5828, and you add sort of like a double dose of engineered crumb rubber, around 10% by weight of the binder, to get back up towards the plan grade of the binder. But we control these mixtures with mix testings, not binder testing. But the idea is that it's an equivalent binder system that gets you the Hamburg result that you want and the CT index score that you want. And then we did the same thing with like plastic pellets, low density polyethylene. That's a pelletized product from that we imported up. Nobody was making it in our area, so that came from Avangard recyclers in Houston area. We had used it before near our campus on a demonstration project, so we knew we could make mixes with it. Medium density, mixed density polyethylene, so it kind of had a mix of low and high density polyethylenes. That was a shredded project from Driven Plastics. We obtained from their Pueblo facility, the blue shred. And then down here with these, we had the elevated BMD with PPA, and then an elevated BMD with styrene butadiene styrene modification. Then on the SMA sections, we had a CT index minimum of 160. Sometimes you struggle to get that. A lot of times you can easily get 300 or more. Kind of really, our rock is all over the place, and these modifiers are kind of all over the place. And then Hamburg, we had a 15,000 pass in this location. Sometimes we use 20,000 pass Hamburg, obviously. So on the SMAs, we had a control with PPA, and then ECR, engineered crumb rubber, and then we use the LDPE waste plastics. So this project was put out for bids. So a lot of times MoDOT, when they do research, we'll have some preliminary research, and then the next stage is to build something. And so we'll let contractors bid on this, and they have to understand that they're going to work with the state research and the university research. it's kind of a cost benefit. The benefit is we did 8 of these 9 mix designs for them. It took a half a year. They just did the control mix designs. And we also help, we bring a QC QA trailer. So we're making gyratory specimens and, staying up all night with them, helping build these sections. The con is that we're in their way, obviously, and we're watching over their shoulder and everything. So that was actually put into the bid. And there were multiple bidders. The successful bidder was Delta. It's a Colas company. All right, so here are the dense graded and, I shouldn't point, this is Asphalt 101 quiz. Identify which one of these is the dense graded mix and which one is the SMA mix. Well, if you've done much with asphalt and design, you'll know that the gap gradation here is a hallmark of the SMA. So that was the gradation there. We use a lot of 12.5 nominal max aggregate size mixes, you'll see. And in that area, we do have a good access to trap rock, and so a mix of aggregates. We do a lot of wrap, so we didn't want to isolate these recyclate materials, these additives, without using the level of wrap that we normally allow on the super pave. We use a lot of anti-strip. We have some issues with stripping, and then the SMAs. We're kind of debating now. We require the cellulose fibers, but we have a new research project that's going to look at whether or not for the engineered crumb rubber, with the swelling of the rubber particles, if we have to use the cellulose. So MoDOT's a little nervous about that and wants to just research that. So that's a research project. So if you look at the mixed performance results, here's the ideal CT test. You can see the super pave control with the PPA, a little bit more stiffer system, more of a rut resistor than a crack resistor system. And then you see kind of the bump that you get with rubber. There you have the swollen rubber particles intercepting the crack faces that would give you the bump there. And then the low density polyethylene mixed density. You got the PPA mix here, and then the SBS modified mix here on the CT index. And we also have the lab mix, lab compacted design pills, pucks that were tested. Plant mix, plant compacted mix. That's where our mobile trailer stayed up at night, and while the mix was still warm, we compacted the mix out of the plant and then let the mix go cold uncompacted and reheat, which is what MoDOT would, or the contractors would ultimately like to be able to do for QA. And but we knew it would affect the score, and you can see that the mix certainly gets more oxidized on that second round of heating, and you can see big drops in the scores in the gray bars compared to the orange bars. So we see this a lot where with the lab mix and the short-term oven aging, a little bit of a pessimistic view on the CT index. The actual plant mix gives you a bump on the cracking score, but then the reheat kind of brings you back worse than where you started. So we see that trend quite a bit. Probably results may vary, so you want to measure that before you build a spec around it. In terms of the disc-shaped compact tension fracture energy test, a low temperature fracture energy test, usually for lighter traffic volume roads, you're looking for, mid 400s, and the medium traffic, higher traffic, you're starting to push your requirements up into the 500-600 range. We don't design on the DCT. We're not a DCT state, except for the fact that I'm there. And of course, I helped invent, and I love this test. But it's interesting to see where we're at with these mixes that aren't designed with this test, because it tells us about the low temperature cracking resistance, and to some extent the reflective cracking resistance, because it's a thermal effect to a large extent that's pulling these mixes in the wintertime. So you can see the super pave control. This is really also kind of a control super pave with PPA. You can see the scores in the mid 400 getting into 500, and then you can see the engineered crumb rubbers and LDPEs a little bit higher, and then SMAs with the thick films, more binder. You can see some benefit in cracking resistance there, but these should be similar mixes. They all pass the specification, and they're probably more similar than they are different, but you do see some differences in the scores, some benefits that can be gained with some of the systems. Then now we have to balance this out against the Hamburg, and we're starting to move towards using the Hamburg to assess both rutting and moisture damage. This is just looking at the brute force rut depths. So you can see some of the control section here, the PPA as compared to Some of the lowest rut depths are in those plastics. We're kind of working on a softened up version of these plastics. We think they work okay as a dry process, but if I was to balance the mixed properties out, I would use a softer version of these plastics. And so we're working on a technology for that, but these definitely get you some good low rut depth scores. And then the only mix that gave us some trouble, and it was seen on the Hamburg, was this SMA control. This is the mix that's used in the rest of the project everywhere else, and it looked fine everywhere else. But on the kind of the time we were constructing the place where we were going to use for a control section, they had an issue with the feeding of the mineral filler at the plant, and actually it wasn't really filling. So stone, matrix, asphalt, where you have a mastic with a lot of fines and you don't have many fines, we were having issues there. They actually removed and replaced a little part there, but we captured that in our testing. But you can see we were doing fine on the 15,000 pass Hamburgs for everything. And then for quality control, after we get these Hamburg designs done, we're thinking about using the RT index, which is it's like the ideal CT test, but instead of having the indirect tension splitting heads, you have more of a triangular arrangement, which creates shear. So it's kind of somewhere between the IDT and the Marshall stability and float, but it creates a fairly decent shearing mode that can score the mix. And it's just a brute force maximum load leads to an RT index. And so you can see, and we've seen this, we had an SMA study before this where our average dense graded scores were always higher than our average SMA scores in this test, which is pretty counterintuitive. Doesn't mean that you couldn't use it for both mixes, but you'd have to kind of have a calibration during the design stage to know what your target would be for the RT index appropriate for SMAs versus dense gradeds. So we'll see where we go with that. That wasn't the point of the study, but we did want to collect that data. And you can see when you do your reheats, you get a bump in the score here, just like you got a decrease in the rutting. It's about a 50% increase when you reheat. So your 40 goes to 60, your 100 goes to 150 on the RT index after the reheat. Tensile strength ratio, TSR, for moisture damage. We want to kind of compare that to the Hamburg results and the stripping inflection points, and kind of in the process of doing all that. But we do have the TRS results now, and you can see that in the 90 to 100 range on these mixes. The control mix was the one that was right on the borderline. So we had different results in the contractor, but all these mixes were ultimately approved and paid, but these were the results that we got from these samples. So the next thing is, now we've built these, and it's been a few winters, and so we specialize in the development and deployment of AI-based pavement inspection tools. And so we wanted to feature that on this project so that we could get out more often than MoDOT would normally get out on these inspections, and we could target our inspections to look at the reflective crack sites and just the overall serviceability of these pavements. And so it's got like a vision-based system. We use camera, we use LiDAR, and then we have a full-blown pavement inspection vehicle to make some comparisons to as well, quote unquote, full-blown, whatever the university could afford. So we have an SSI system with a pickup truck that you'll see that we compare some of our international roughness index and some of our other scores too. But nice thing is you can feed all this data. You get 100% coverage of the pavement. You can put it on a big data analytics dashboard. You get LiDAR point clouds and all kinds of fun stuff. But it's a very mobile system, a couple different setups. It depends how far you're traveling and what all can fit in a suitcase. If you're on the road with this thing, it can be as nimble as this, or a little bit more complicated like this setup that we used in Hawaii last summer. And some distress detection examples, all different types of crack types that you delineate between, whether it's longitudinal, thermal, reflective, or block. You can pick up raveling, weathering, and you can pick these things up at different severity levels, because we're trying to feed this into ASTM PCI standard, and we want to be able to do that accurately when we compare it with manual surveys. And so this is something we've really honed over the last 5 years. The AI will do a lot of things. We have different types of AI. Some are more just kind of classification, where we'll draw boxes and we'll identify features. You know, it's an alligator crack at low severity or a transverse crack, medium severity. We have other AI models that put little dots and pixels and sort of count the crack width or average crack widths, using a completely different AI architecture. Then we kind of fused the two together because with distresses, you're trying to get type, extent, severity of distress. So sometimes you'll have to use multiple tools to get there if you want to automate it. Our SSI inertial profiler looks like this. And so here we just wanted to make sure that if we indirectly computed rut depths, let's say from LiDAR point clouds or IRI from LiDAR point clouds, that we could verify it with a more direct laser measurement. So that's some of the kind of like a little bit of a side study we're doing with this. The IRI data, and when it's more granular, it looks like this. You can break it into 1/10 of a mile segments or 500-foot segments like that as well. And probably don't need to get into great detail about the software that comes with the machine, but we've kind of zoomed in here below 80 on IRI. You know, when you're down here in the 50, 71, it's probably asphalt. You probably don't get this with concrete from day one. And two, early in the life of the pavement, where you're just talking about a year or 2 years after construction, you don't see a lot of movement. We see more seasonal effects. Turns out that this was jointed reinforced concrete, which we don't have a lot of in our state. We have a lot of jointed plain concrete with narrower crack spacing. Here, these were longer joint spacings, jointed reinforced concrete with some mid-panel cracks. And you can actually kind of see, I think, some of the movement seasonally of the concrete is affecting the ride as much as the asphalt and little pops that you're getting with an occasional reflective crack and really no other distresses. So the pavement condition indices are still, above 90, and most of them are above 95. I suspect that these will start to go now that we're in, the third winter. But mostly what we're seeing is like low severity reflective cracks right over where those old joint sites used to be for the concrete pavements. And, got nice HD pictures with downward facing camera, the box around these. We will close down this pavement and do a foot on ground survey once we get enough good stuff to look out there so we can check and maybe recalibrate the AI system. But it seems to be finding everything and scoring everything well. There was some horrendous issue going on with one of the concrete joints there, and we have good imagery of that before the overlay. And sure enough, it's created a crack that's like spitting out chunk of stuff, but it's like one joint on the whole test section. So we kind of keep an eye on that one. And then as far as like rut depths, we're talking small. The SMA controls, the mix we had a little bit of an issue with, and the contractor did, and that's the one that's showing a little bit more rutting. But luckily, there's a cracking study. The last thing you want it to do is die in rutting. You try to fix cracking, pendulum swings, and you create a rut-prone pavement. Balanced mix design told us we shouldn't worry about rutting, and it doesn't seem to be an issue. Okay, doing okay on time. So as a modeling update, my colleague in the structures group, Oliver Giraldo Londono, he was actually a student at Illinois when I was a professor there. I left and went to Mizzou. He had a co-advisor, Glaucio Polino, that's worked on some stuff with Minroad before on a pooled fund study. He left and went to Georgia Tech. So Oliver followed him down to Georgia Tech, got his Ph.D., and we were looking for a structures guy. So then we hired him at Mizzou. So it's a small world after all. And Rogelio was one of his students. He's from South America. The modeling goals were to develop finite element models using kind of a new version of our cohesive zone model. We worked with the cohesive zone model way back on the low temperature pooled fund study in the circa 2006, 2010. And those have really taken off ever since, and they've become pretty easy to implement and much more powerful. But we have a new implementation of that and kind of calibrate and validate with field performance. We're kind of working on the calibration now. By the end of the study, we will try to validate it. So you have smeared versus like discrete approaches. So cohesive zone models, classic, you had to model the crack. You either had to know where it was going or at least put in the elements that facilitated a discrete crack somewhere in the direction of where the crack would go. But you normally didn't want to put them all over the domain because of a couple of issues, and probably don't need to get into that. we started working on phase field methods. You know, the old smeared crack models like viscoelastic continuum damage models, you kind of soften all the material in an area, and that's how you damage the material. Like for distributed fatigue cracking, that might work out. But for this really discrete reflective crack problem, you'd like the crack to be, the energy and all the damage to be located in that one area, and you'd like to predict the crack propagating. So this phase field method, it kind of gives us the speed of more of a smeared cracking model, but it allows us, we can kind of couple it with the cohesive zone model concepts. And so when the crack forms, it's a real discrete crack. And so all the equations, all the thermodynamics are pretty much respected with that. So on the phase field model, the first thing we wanted to do was to model cracking in the DCT fracture test. We do some homogeneous analysis where we just kind of use the average property that we get from the DCT test across the potential crack face. Then we ran some simulations where we actually put coarse aggregates in the microstructure. And this is an example of where the crack was sort of dodging around some coarse aggregates. And we get the predicted load CMOD curve that you normally get from that test. Here's a cohesive zone model where we just put a standard row of elements that we're able to separate and stretch across the crack face. It gave us a nice straight crack face. So this is kind of like the modeling we were doing 15 years ago. Then we started to implement the phase field model in both the mixed test and the pavements simulations. And so this is the kind of thing we're modeling. You have some kind of a subgrade system, some existing pavement system here. You see 2 PCC slabs. So this is kind of a elevation view looking in, and this is the longitudinal direction of the pavement, like looking at it from the pavement edge. And then here's the potential reflective cracking site. Temperature movements create that tensile mode 1 crack. As the wheel rolls over, you get sort of a double shearing mixed mode. Actually, at the edge of the pavement, you get like a mode 3 tearing that's often overlooked, but you know, we have all 3 modes of mixity here that we have to potentially be concerned about. We don't capture them all in a 2D model, but it is a good start. So here we started with a cohesive zone just to get to work quicker on this. Eventually, we'll put the phase field model in with the actual aggregates, but a step at a time. And then there is some load transfer efficiency. So we went out and hit these with FWD, all the joints. Before we overlaid it. So we can kind of back calculate the load transfer efficiency with some kind of a shear transfer element there. And we're using default values now just to get the model converging and working. But then we'll eventually, when we calibrate the model, we'll get it to match the FWD results. And then we'll put the overlay on top of it and predict the cracking. And eventually, we've done this on the mixed test, but on the pavement simulation, we'll put in the coarse aggregate as discrete aggregates, and then we'll also have the mastic system, and we have some lab measurements of mastics in the past, and we'll when we get time, we're going to do a little bit more mastic testing on these particular mixes so that we can get the right properties in all of these elements. We had to build master curves, getting creep compliance testing at different temperatures. This is kind of classic stuff I've been doing for 30 years. I used to use the SuperPave IDT. We actually can get these creep curves from the DCT test. We have a paper on that, and we're doing a lot of it on this study. They can be nice, pretty looking, smooth curves. That's one way to tell it from the IDT. It's just kind of the smoothness of the curve. It's a larger displacement. So this is that mixed density polyethylene mix, master curve. And then you can use interconversion techniques to get the relaxation modulus. And once you interconvert it correctly, then you can fit like a Prony series model to that. Here's how you can tell it's the structures group doing it and not my group. I don't put the E infinity on there. I don't think we ever don't have some kind of compliance in the mix or rheology in the mix, but it does help you get sort of that asymptote there, so that's fine. Numerical modeling of the creep test. And so this is the DCT creep. So the way it works is normally in a DCT, it's just a millimeter per minute opening and drive the crack and measure the load and the CMOD. and you get the area, and then you can get the fracture energy from the area. This one is you put a fixed load on, like a IDT test or a bend beam test. And the modeling, I know this could be a little offensive. The modeling people don't dislike us, but I need to tell them force is F, but displacement can be delta. Like, we don't have to put FU on every slide. And so it's no offense to y'all, but U is often used for displacement. They just think nothing of it. But here you can see the 3 replicates on the different mixes. Some of them repeat nearly perfectly. Others, you see little differences. Could be a big rock in the crack face or an air void or what, just the normal variability of mixes. But you hit it with the fixed load and you let it creep. And those are the kind of curves you get at 0. You're going to get more slope, -12, -24. And that's how we can average those to get the creep compliance that we can use for the master curves. And so here's just a little bit more on the numerical modeling of the fracture test. This one is the, now we're using a phase field model, but with a straight crack path with the MDPE mix. And you can see load CMOD curve. The way we pick these bars, you don't really see this red action until kind of the end of the test, but you have a fracture process zone that opens up. We did a size effect study with Mike Wagner way back in the day that showed that, you know, you get into like 30 to 40 millimeter fracture process zone size, but luckily the DCT has an 81 millimeter ligament. And so you can allow all these processes here of loading, you start to damage and you start to get big damage and softening. You capture it all and you move that for a while before you start to compress everything at the end of the specimen here. So you get a pretty rich crack face. And description. Here's the experimental range from the mixes. There's the numerical results. So this is kind of on our calibration phase. To get these things to match perfectly, you can play around a little bit with the constitutive model for the traction separation or force displacement. But you can also do a heterogeneous analysis where you're bumping around aggregates, and it tends to be a little bit better match. So we should see that when we employ the aggregates in here. And then going to a full 3D analysis is where you finally can get your best curve matching. But this will be good. We have to make sure that we don't get too fancy before we go to the pavement simulation, because the pavement model is huge and it's going to be pretty expensive to run. I'm pretty excited that we're kind of moving towards a phase like where quantum computing is maybe going to happen before I retire, where we can get our hands on that and just like do everything in 3D. But until then, we have to be a little careful. The other thing we're doing is we're taking AI and we're trying to learn how to inverse big matrices, like for structural problems. And so maybe either AI or quantum computing will allow us to just turn all the physics on these. But for the meanwhile, we've got to take it a piece at a time, and 2D simulations are fine. But just to see, we've been working on these different mixes. Finish up here in a minute. You can just see some of the preliminary modeling. First, we'll start with elastic, and then we'll swap out the asphalt properties for those viscoelastic master curves and fracture data that we have in our test. This is just to make sure that we're building the model right and doing some initial validation of the model. So we threw a couple load cycles on it, and we'll kind of zoom in there. And so you can see we're able to drive a crack through the asphalt overlay in a, this is obviously a vertical load simulation. You can do the same thing, temperature simulation. You won't have nearly much vertical displacement, a little bit, but mostly just horizontal opening. So this is the kind of a load simulation. And so a couple of high fidelity finite element models have been proposed by this collaborative team. We have predefined crack paths, and the fracture parameters are calibrated using inverse analysis and DCT tests. And then we're working on a model that explicitly represents the mastic in a coarse aggregate system in a defined area of interest. So we won't put that model all over, but we will put it right over the concrete joints so that we can capture the richness of that. Because what we ultimately want to do, and maybe the next time I talk, I could show you this, we want to show if there's a difference between like rubber modified asphalt, plastic modified, PPA, SBS with not only the crack rate and the crack opening, but with the spalling, because we're going to be measuring the, the crack widths versus time. And maybe we can couple what we measure in the lab with what we're seeing in the field, so that in our designs, we can better take credit for mixed designs that, while they may allow reflective cracking, the severity levels may be, well, first of all, the crack appearance could be delayed, but then the severity level could be lower, and you'll have less maintenance liability, you'll have higher pavement performance. And I mean, it may be a subtle thing, but it could be the difference between choosing one material versus the other, or whether you go to the effort of trying a fabric or a grid or stress absorbing membrane interlayer, or just try to build a mixed system that is the best value proposition. Might crack, but it might give us the performance cost that we really want. Right now, if all we do is predict when the cracks occur, for one versus the other, it's helpful, but it's not really the whole picture. I guess if we thought we were going to move towards a technology where you could put asphalt over jointed concrete and never get a reflective crack, then we could still focus on that, and it may eventually get there. But a lot of times that's not the only goal. We have a lot of constraints financially and other goals with the pavement system, other serviceability that needs to render. So sometimes we have to live with some of these reflective cracks, but sure, it'd be nice if they weren't really gnarly, if they were really spitting out a lot of mix and needing a lot of crack sealant and things like that. So we'll be calibrating the properties in the DCET and eventually the CT test, and we're putting those into the pavement models. And then we can look at different scenarios. Once you have the model built and calibrated, it's less of an extrapolation to look at what would an extra inch of asphalt thickness buy for you. If you've calibrated it for a 2-inch thick system, you should do a reasonable job predicting what would happen with a 3-inch thick versus an 1.5-inch thick system, and maybe try some other mixes in the lab, and then kind of have an idea of what they're going to do in the field before you build it. Maybe throw an interlayer in this model, and just kind of an integrated mixed pavement design for overlays with reflective cracking and severity levels considered. Again, probably you're going to need a pretty good desktop computer to run these models right now, but at the first time in my career, I think that these tools could be on the desks of a practitioner, in the short run rather than the long run. So we're pretty close to being able to have models like this integrated. Maybe in the next, revision of the Pavement ME would be really nice to have more of these models and more of these advanced tests. So we're working on our E-star master curves. We'll compare those to our DCT kind of inverted master curves. So we have a bunch of DCT creep data. So if you want to know more about that, we had a paper on that. You can have a copy of these slides. That's a QR code will take you to that paper on DCT creep. And we'll continue to monitoring field performance. This is the part where you get those S curves, where if you look at percent reflective cracking versus time, it's got like nothing, little bit, and also it's like woo, a lot of cracks. And then you're like 100% reflective crack after X number of years. Hopefully, it'll be 5 or 6 or 7 years rather than 2 or 3 years, which is what we often get in the Midwest. But we'll see. We're definitely going to see more cracking, and then we'll calibrate our models accordingly. So I'm going to see what Mr. Chairman wants to do time-wise. I think I did okay. And are we going to take our questions now, or just kind of wait till the end of the session? Maybe 5 minutes or so. All right, let's do any questions.
Any questions for Bill?
So is there a reason for not doing a bracket seat on the existing concrete, or did you just use the jointed?
That is sometimes used in our state. They wanted to be part of the reflective cracking challenge, so we didn't necessarily want to study that in this study. MoDOT is letting research on rubbleization, so we do rubbleization, and they're interested in studying that. So it's kind of a time where we're trying to get more research data on that. But that really wasn't the goal here, because a lot of times the overlays are put right on the concrete like that.
We have project, we do the bracket sit on the existing PVCP, And for the air of fabric, webbing course on the top, we use some mixes for the reflexive crack. So I was just looking at that kind of strategy.
You know, Missouri bragged for many years about being the lowest mixed ton cost, for mixed ton state in the United States, probably because we're a PPA state and not SBS. But the budget's pretty limited. We're also a balanced budget state, and I'm not trying to pick on you, California, but there's only so much money to go around, and so our solutions tend to be pretty thin. Like the last demonstration I did was 1.5 inches on concrete, Stadium Boulevard. Now, we probably don't have the traffic you have, and they don't last as long as you do, but we do build a lot of rehabs on the cheap, if you would. It's just the reality.
Usually the rehab projects, this is how we enjoy the rehab project.
Depends on the budget. Like sometimes they'll go for a longer design, like basically like almost more of a reconstruction, try to get a new 30-year period out of it, and that'll be a rubblization job. We do more rubblization, I would say, than crack and seat. Yeah.
Right?
Yeah.
On this bracket, we just by
Sure.
trees. So we go the deflection bracket just to distribute the stresses. That's how we typically do when we use the rehab project.
I mean, the work that we did in Illinois when we compared crack and seat to rubblization is that the rubblization would completely mitigate any reflective cracks, but the crack and seat, we would get some reflective cracks. But there's a difference in our climate is nasty. Yeah. Well, it depends. The project that I did in Illinois, it was kind of a lower easel, like 1 million easels per year. And that one we researched 6, 8, and 10 inches on rubblization, and they all performed pretty well. But there was definitely a benefit in the thicker ones. They stayed smoother longer, but we didn't have failure in the 6-inch section. And that was with kind of like a neat stiff binder. That was way back in like 1996. That one. But Missouri's, it can vary. It depends on the traffic. Our traffic really varies from our urban interstates to our rural interstates. Big differences in traffic.
We have a original thickness threshold that has to be rubberized.
We probably do, but I probably couldn't tell you what that is.
Oh.
Yeah. And it's about to be redone anyways, because we've become like a pavement ME state, and so we're in the process of calibrating that design system. I imagine whatever we have now is probably poised to change in the next 5 years.
You don't have a computer accounting for the variation of your software conditions in your modeling. How long does it take to run 1 month? Just connecting with the federal highways, and let's talk about how we're trying to account for uncertainty, variability in your foundation, because soil is variable, right? So are you, in your future work, are you trying to attempt to account for the variation in your software?
I should have included that in my list. So, yeah, of course.
You
Yeah.
can provide that variation for preventive conditions. So I think will inform your model.
Yeah, they just take a few hours to run.
Already.
Yeah. So it'd be possible to do a parametric study on that. Yeah, for sure. And that's important because we're also looking at high mod, and we haven't really done much with it. But one of the things with those designs is that there's pretty strict subgrade requirements for that. So if you don't have a certain CBR in the subgrade, then you have to take some remedial action, which might mean like 12 inches of rock before you even get going. So 12 to 18. So that's probably something that needs researched because, we're a state that invites concrete and asphalt for new construction, but lately I would say concrete is winning on the designs. So the asphalt industry is trying to figure out a way to start winning more on new pavement construction. So evaluating all of these things that we're talking about, rubblization can be part of the reconstruction of I-70 and I-44 because we have a lot of concrete there. And if we don't have highly calibrated models for rubblization plus, let's say, high mod, then we may be putting way too much asphalt down.
So, Blankenship asphalt too. We got to work on these things a long time ago. And I guess the question I have is that, are you taking what was done back in 2002. And now reloading it where it's not the off-the-shelf model. This is the customized models to help us through the reflective cracking. And if so, you're talking about being desktop, that would be great because currently there's no button we can slide to handle reflective cracking. So it'd be a great way to model these scenarios.
Yeah, the way we're doing it now, there's not much difference between the cohesive zone model and the phase field model, where we need to get away from the old cohesive zone model. We can use that for validation now, actually, before we move on to more complicated things. But when we have like multiple cracks going through the mix, that's where the phase field will really be more efficient and it won't have as many convergence problems. And then you can just kind of go from there. Like it'll be able to handle the opening and shearing. So like the simultaneous temperature opening, and then you hit it with a tractor trailer. The phase field model will be good at letting the cracks go like this, like they do. If you ever cut a pavement on the side, look how a reflective crack goes up. It's not straight up. And with the strata, with the SAMI, it would hit the strata, maybe nothing would crack, or maybe go over a foot or two, and then it goes up there. It's like, what model could predict that? But I think the phase field model could easily show that.
Okay, sounds good. Thank you, Bill.
Okay, thanks, everybody.
Okay, next presentation will be from Dave Johnson from the Asphalt Institute, and then he's presenting on Utah high mod asphalt mixes, which are rapidly becoming a popular asphalt mix.
There we go. Thank you. All right, should be good. All right, well, following Bill is always a high challenge. He always does such a great job, and I really appreciate the work that he's doing. This is a very hot topic. Excuse me, I believe this is my 6th presentation this year already on this. And so I will be making my way through this in fairly rapid order because some of you may have seen some of the other slides before, but I do have some new information in particular as it relates to cost differential of different mixes in Utah in 2025. And so there is some new stuff coming, and there we go. So we'll talk a little bit about what happened in Utah. As you saw in the title, Montana has also dwelled into this technology. We'll give you a few slides on that towards the end and let you know what's coming up in other Western states. But this is such a dynamic field where various states are looking at it. They're thinking they might do something this year. It's getting pushed to next year, or they're talking about doing it next year, and all of a sudden there's a project that they're able to jump on. And so some of the dates that I'm going to show towards the end are already changed. I just found out one today. So I'm not going to play Howard's video because we don't have time for it. Basically, Howard says I'm cool and he likes what I'm saying. Trust me. All right. So this technology in Utah initially was used not only with the highly modified and adjustments to the volumetric criteria, but they also put it down in the thick lift configuration, as we'll see in the Port of Wendover. And so we need to give credit to the state of South Carolina in particular for some of the work that they have done with thick lifts along their eastern seaboard and the work that they've done at NCAT. And they have successfully laid as much as almost 8 inches compacted with very good densities and good performance. They did that for speed of construction in some of their high tourist areas. They, of course, if you're working in the world of asphalt and it's anything of any sort of importance, NCAT probably winds up getting their fingers into it, which is a very good thing. Both the state of South Carolina, as already mentioned, and Creighton sponsored sections at different times at the test track, both with modified and unmodified material. Unmodified with South Carolina. Creighton, of course, was with their Hayti system. Both of them had great densities top to bottom. The Creighton section, which only went through one cycle, was less than 6 inches in thickness, but it was behaving in a perpetual fashion. That was a 3-layered system. They didn't put it all down in one lift like they did in Utah. Utah concentrates a lot on the Humber, and they did a significant amount of lab work in preparation for field trials with this material. And they began by looking at the Humber with a double cycle. There are 20,000 cycles stayed at 50 degrees, and they ran the typical 20,000 cycles, and then they added extra weight to the wheel and ran for another 20,000 cycles. With none of those mixes, and they started at a design value, went up in 0.5% increments all the way up to almost 7% binder. Even after 40,000 passes, none of them had even close to 10 millimeters of rough, which is their criteria. So in 2017, They took some of this binder and put it as a substitute for a 64-34 super pave design, throwing in the 76-34. In one case, it was a master grade. They were able to successfully put this material down. It had performed quite well. They did their typical thicknesses, and everybody was happy with it, so they moved forward. I want to show you a couple things about the Utah binder spec, starting with they are a unique state. They're the only state I know of that has an unaged G-star requirement 1.3. They do that with all of their binders at their upper PG grade. So if you're a 5828, you have to have 1.3 or greater and 58 degrees. In this case, we're talking about 76, so 76 degrees, 1.3. The other thing, and I don't have it highlighted here that I like to point out, it's a standard rotational viscosity requirement of 3 max. And so not only do you need to be stiff on the unaged binder, but you still got to pump it. And the formulators, Idaho Asphalt deserves the credit. Dave B, if you know Dave, he's the one who did the initial formulations of binders that they are using in Utah. Others have followed suit. They have done an incredible job of creating a very balanced binder that not only does it have that stiffness, but it's still pumpable. Most of their binders, SBS states, most of their binders are lining up at about 5%. As a comparison, the Craton HIMOC is a 7%, in some cases greater SBS loading. So we're in between, if you will, the typical SBS loadings that you might see with materials and the HIMA system right here is a bit of a sweet spot for Utah at 5%. To help visualize this, Howard's lab produced a couple of videos, and I do want to take the time to see these. Hopefully we can get them to play. And if not, trust me, they were very cool. They don't seem to, when we brought this up just a second ago, it said there was an issue. I think we found the issue. So essentially what he did is he, oh wait, here we go. I guess you push the button enough times, eventually it'll go. We got 2 videos that we're going to show, and maybe we skip to the next slide. This is the elastic recovery. As we can see here, 4 different binders. The binder that we're most interested in is down here in the lower corner. On the device itself, there's only room for 3, so we're only going to pull 3. It'll be in building port 4. Anyone want to guess which one's the modified material? This is not a quiz. And this is the one that I really want folks to see. If you haven't seen this one before, we're starting off with a standard neat asphalt 5828. We're dropping this thing right at about 0 degrees Fahrenheit, 18 degrees C from a countertop. The middle 2 were typical modified materials. Now really pay close attention as that thing hits. I need to slow this thing down because that beam actually bends at 0 degrees when it hits the floor. Just a little chip fell off it. So we take this thing out to the field. The location where this is at is at the Port of Wendover. If you're familiar with the bottom of the salt flats, I see some people shaking their heads. This is where we set world records for land speed. We're not setting world record for land speed with our speed of construction here. We're hauling this stuff for a couple of hours from a plant just north of Salt Lake City across the state, and we're going to lay it down in one single lift, compacted thickness of 6 inches. This is not a high volume location in terms of the raw traffic numbers, but over 50% of the traffic is trucks, which means 2 to 2.5 million easels per year at this location. Very hot summer location, quite cold in the winter time. If you were to do a 98% reliability with our standard software, it would come out as a 6428. So we're stretching it on both ends. As we mentioned, 6 inches. This is a bathtub essentially because they milled out existing PCC, only around 330 tons. Highly modified, dense graded, constructed in a single lift with a 2-hour one-way haul. Here are the design, mixed design for this particular project. Staker Parsons was the one who built this, and Idaho Asphalt is the one who supplied the materials. It is a 12.5 millimeter mix. It is a fine mix. Every time I build this look at modifying this presentation. I put a graphic in that shows the gradation, but I run out of slides, so it goes away. There's around 63 or so % passing the number 4. So it is on the fine side. 100% crushed material. They do allow wrap in the surface, which is the first for the state of Utah, at up to 15%, which means about 12.5% binder replacement. They are designing to 1% airborne. 75 gyrations is their normal. On this, they go down to 50. If you were to take it out to 75, you're going to be pretty close to a 0 airpoint state. They have a VMA range of 15 to 17. That means you're over 90% on your VFA. Very rich state. Because it's so rich, they do a drain down test as well, just like you would with an SMA. Never had to have that problem. And there's the Hamburg results for this particular mix. 20,000 passes at the standard temperature, but instead of adding extra weight like they once were, now they're cranking the temperature up to 54. They have not had any issues, and so for flat logistics as much as anything else, they only do a single cycle now at the 54 degrees. Still no failures. Also, after this project came in, they recognize that their aggregates do vary, and so they just pulled from their SMA and minimum asphalt content based upon the gravities of their rock. Most of the rock that they're using are to be on this lower end. The first project, as you saw, had a minimum asphalt content requirement of 6%, and lo and behold, Staker Parsons designed exactly to 6%. And that was total binder, not virgin. Some more information and detail about the Hamburg. These are the graphs that came from those 20,000 cycles. Somebody find me a stripping inflection point. If you find it, I'm going to question your ability to judge a stripping inflection point, but there isn't one, of course. Staker Parsons was quite nervous. 6 inches of compacted thickness on a single pole, can we actually do that? We do it well. So they decided to lay down about 100 tons of mix on their dime and do a test strip. This is their scale house at the Beck Street plant, which is on the north end of Salt Lake once more. Throw this thing down. And remember, I said it was going to be built in a bathtub out at Wendover. This is unsupported edges. Pull 12 foot, standard vibratory rollers, seeking to get 96+% density. They had some feeding issues. Had a zero haul essentially. The plant is just out of sight here. When you're trying to put that much material through a paver, you better have your trucking on board, and they better be on time. What did they find out? 97% density was easily achieved. Regular rolling equipment. Anybody care to guess how many passes the breakdown they used on this mix? Somebody guess. Come on, we got a lot of people in here. What's that? 4. Anyone else? 2. 3. They did 5. But they had no intermediate roll. And they had to wait and wait and wait finally got full enough, and they finished it. So 5 passes, breakdown roller, unsupported edges, granular material that's hard as a rock, by the way. And they reached 97%-ish density, top and bottom. Mix was very stable. This is the thing that really surprised me. You got unsupported edges. We're putting a heavy roller out there, and the thing, it grew slightly, less than an inch. I was very concerned about this thing creeping out, and it just didn't do it. So no significant issues were encountered. Take it out, a 2-hour one-way haul. We were 300 degrees at the mix temperature at the plant. Lost about 25 degrees in those 2 hours. Hate that tack coat, by the way. That is the largest windrow I think you will ever see in your life. Quite frankly, you could not produce a bigger windrow. If you needed to go thicker, you'd have to go narrower on the back of your street. This is looking back into the state of Nevada. Again, ignore those tack coats. This is the downstream side from the scale. You saw that picture already. They fixed their feeding problems until they had a truck that lost a tire on the way over, and so they had about a half-hour delay. Here is the cooling curve. There is a temperature probe that you can still go plug into and get data from if you'd like. It took a long time. You got that much mass, no big surprise. It just took a while. They were concerned about opening this up to traffic. And so this paving happened on a Thursday, and they did not open to traffic until the following Monday, because the regional materials engineer, he was the one who had to say, go ahead and open up to traffic. And guess who doesn't work on Saturday and Sunday? And so that's how that happened. Here are the densities at Wendover. They held the contractor to the pre-WL standard on the top half, but measure the density on the bottom half. This is where that truck had that issue. So that mix had cooled some, struggled a little bit to get density at their targets, but we're still pretty decent densities there. This is a picture I took in October, 3 years after construction. People ask me, is there any running out there? I said, oh yeah, there's at least 1 millimeter. Basically the film thickness got wore off. There's just really nothing happening out there. No cracking, no distresses of any sort. We have exceeded over 6 million trucks now. By June of this year, it'll probably be getting pretty close to the 7 million number. Very, very good performance. Skid numbers is a legitimate concern, but those of you who are familiar with the mixed busters articles that Buzz and I are doing, we actually have one coming out this time on skid numbers and safety. This is just one aspect of safety. The reality is this is a fine graded mix, and so yes, it has good macro texture, relatively speaking, because it's 100% crushed material. However, it's a fine graded mix, but you do have a good skid number. In the years following this installation, they kind of dipped their toe into the water a little bit more. And these are some of the different locations. One in particular that we'll talk about is an overlay on Interstate 15, very close to the Beck Street facility. If you're familiar with the Salt Lake area, you know where the lagoon amusement park is, you're right there. And so in the northbound lane only, this was an existing Portland cement pavement that had done good service for the state, was due for a crack and seat operation and then overlay. They decided, let's see what happens. They just went out there and sealed the cracks on the concrete, swept the thing, and overlaid with 3 inches of this material, the exact same mix. Great densities, as we can see, an average of almost 97.3. The only thing I don't like is this had been planned from the get-go that they were going to overlay with an SMA, which they did, 24, which is fine, except now I can't see this mix. And so visually, I lost that. That had great performance. 2024, things really opened up. We had over 500,000 tons of mix. We're going to go through every single one of these projects. No, we're not. We're going to go through this last one, which is now being constructed right now. This is a reconstruct of Interstate 215. It's a beltway around Salt Lake City. This happens to be a stretch of it that's essentially just south of the airport. The original plan had been remove and replace the existing PCC, which again had given them decent performance. They decided, because of the great performance they got, they wanted to do an alternate design. And so they went in and said, let's rubbleize this and let's put down 5.5 inches of this material. And what does that mean? Well, as it turns out, it means about a $40 million savings. And so they took that $40 million and stretched the project 17 more miles doing ramp. Granite was awarded this last fall. Rubbleization will be happening at the beginning of this next month in May. And so that's where they're at in the staging of this project. It'll be completed not this year, but next year. We collected some mix and took it to our lab. And the mix that we collected was from the Back Street operation and ran it through our beam fatigue. And this is limited numbers of tests. I'm not in any way saying that this is a lot of data and we got all kinds of strong conclusions from it, but the trends are definitely there. The one that I point to most routinely is this 64-34 mix, where we ran it at 600 microstrains and they got a little over 12,000 cycles. That same microstrain with the highly modified material almost made $1 million. We got a little over 900,000. 72 times more cycles built at one level, at one temperature. Take it for what it's worth, but that's a notable difference I think we can all agree on. There is other independent work that's being done. The Federal Mobile Test Lab was just across the border in Wyoming, and they collected some material and did some Texas overlay testing. Once again, 64-34 super pave mix compared to the high mod mix. Quite frankly, we didn't see a whole lot of differences in those results, which is pretty consistent with some of the work that others have done. Down at the Corps of Engineers in Mississippi, Dr. Ben Cox and his team has collected some of this material. They got an extensive amount, probably more testing than anybody has done on this material. And in some conversations with Ben, they're don't really want to say too much about it, but we're very excited about what we might see from them. There's some other independent testing that is being pursued. We may wind up doing some more testing in our lab as well. What have we learned so far? The target density is 96%, and the contractors have not had trouble meeting that requirement on their map. The joint density is 94%, and in general, that has not been a problem either. The mix is very stable and workable. They've used it in a wide array of projects from bridge overlays, and now they have one project where they laid it down 9 inches compacted. I'm not supposed to know about that, but they did. So if you see Howard, don't tell him I told you that. 20-fold increase of this material in 2024 from all the toe dipping that they did before. In 2025, they had a 56% increase in the amount of material that they put on the ground. In 2025, 2/3 of their mixes on their mainline highways was high mountain. It is their dominant mix. They hauled it as far as 6 hours one way and successfully laid that. That again is from the Back Street plant all the way down to the Four Corners area in southern Utah. The one-time biggest proponent for more concrete, who just retired in December, was switching projects to this. Cost data, 2026, the high mod had a 6.6% premium compared to our base of 6434 super pave. SMA was 27% more than the super pave. Contractors love this material. If we look at the share by year, notice that 2024, it started to grow and it overtook SMA as the most popular tonnage. Last year, again, 2/3. Look what happened to SMA. Not 1 ton. There is a couple of SMA projects that are happening this year, so it hasn't completely gone away, but in 2025, maybe it's a blip here, but there was no SMA in Utah last year. Cost-wise, this is that data that I showed you for 2024. I now have 2025 data. Let's talk a little bit about that 6.6. How can it only cost around 7% more for a much more modified material that is getting about 1% more binder in the mix? Well, don't forget, they got wrapped. So the actual virgin binder is not that much different than traditional mixes. A few tenths higher, perhaps. So far, the suppliers haven't been charging much difference between 7634 and 6434, but they did see a little bit more of an increase this last year in 2025, 11.3% difference. So from 6.6 to 11.3, almost a doubling of that difference, if you will. Keep in mind, this is their go-to mix now, so you've got economies of scale working for it in their state as well. I said density has not been a problem. They had one project out of 50, this is 43 projects that had an issue, did not meet the 96. Their bad density was 95.6%. Terrible density, but it did meet their target. Longitudinal joint at 94, that could be a real challenge when you start getting thin. The contractors are cutting those joints back on 2 inch, for example. 1.5 inches, they do not hold them to this joint density. They do hold them at density. That's how the state is laid out. Notice that 1 to 4 is north to south, south being quite rural. That is a location where they had a 200,000 ton project of this mix that began last year, got most of it down. They got a bit more next year. All of their regions, with the exception of their northernmost region, it is the most popular mix. What else is happening in the Rockies? I'm sure that our friends from MVP in the back would love to talk with you about the North 19th project. We are a master state. The original intent had been a 9.5 millimeter mix, which Utah, by the way, now has a spec for. The contractor, good local contractor, they were awarded the project at about 75% of the engineer's estimate. Give it a bit more on that in a moment. Idaho has been looking at something. They've had a project, they pulled the project, it might happen this year. Colorado has a project that will happen this year near Rifle. North Dakota has a couple of projects that sounded like they were going to happen this year, but that's the one I found out just a little bit ago is going to be delayed probably till next year. A couple of slides from North 19th, beautiful location in Bozeman. That's where the Montana State Bobcats, of course, live. Go Cats. The contractors, mix designers struggle And I have to admit, and I think my friends in the back will attest to this, we do not have a single good mix design consultant in the state of Montana right now. It's the sad truth. We have a tremendous one whose wife got brain cancer and retired. And unfortunately, there hasn't been a good person step up. They were really struggling with the Hamburg requirement. And of all the different mixes that I've troubleshot, quite frankly, this is the easiest one I've ever seen to be able to tell them what the problem was. The aggregate structure was not good, and they had way too much binder in it. From with the Hamburg, who saw that coming? So about 2 weeks before the project is to start paving, there was a massive switch. The contractor got about a $500,000 change order, and we just basically cut and paste the Utah spec for the North 19th, went from a 9.5 millimeter to 12.5 millimeter. Everything else, like you saw in Utah, was required as well, including the G-Star requirement. The binder supplier didn't really have time to do what they needed to. And they were able to meet the G-Star, but they could not find the rotational viscometer numbers that they needed. That's going to create a major problem of choking the plant here in a second. Quite frankly, this binder would not have been accepted in Utah. Howard and his team would have rejected it. So what happened? Because of that stiffness, they had rotational numbers that went as high as, I think, 9 in the field. I see some head shaking, yes. And so this 400 ton an hour plant never exceeded about 180 tons. Nighttime paving, slow to begin with, took them 3 times as long to pave. So the contractor wasn't very happy when you're out there talking to them, but now they've been asking, the same contractor been asking to implement this in some other projects. So they think they have a competitive advantage. They did get good densities. The rest of the project went pretty well, except that it was slow. I mentioned some of these already. I don't want to take up any more of Eshan's time. Thank our members. I really think this is a game-changing technology. I think that SuperPave is evolving. When we talk about balanced mix design, Howard likes to refer to this as balanced mix design on steroids. And I think he's got a very strong point. One of the advantages, I consider this an entire system. People think about the binder, and that's fantastic. It's right, it's good. We should think about the binder. But don't forget, they're also making notable and areas of adjustments to the volume metrics that we once thought were impossible. Designing to 1% air voids, we would throw up our hands and go, that's going to rut, and it's going to have all kinds of problems. We're going to have shear flow, it's going to flush. It's not doing that. This is a stiff binder. So when we try to implement this technology elsewhere, we got to make sure that we have a binder that's stiff enough for your location to give you the right properties, so that we still can make the right adjustments to the mix. And maybe going down to 1% isn't the right choice for Missouri. Maybe going to 2% air voids might be the right choice. But 4% or 3.5%, I can almost guarantee you that's not the right choice anymore. I don't know where we're at for time.
Anybody have some questions for Dave?
Thanks, Dave, and great presentation as always. Just quick question. Seems like 3 to 4% in place as a starting point. Have any of these projects been tracked as to how they are evolving density wise? I know there's no rating issue, but just in terms of.
No, it has not been any of that follow-up yet. The anecdotal evidence at Wendover is it's not densifying anymore, because it's not moving. So, there is a project that I didn't mention. It's one that was very problematic. It comes out of the mountains and it hits a stoplight, and there's loaded mining trucks that have destroyed pavements. They put 2 4-inch lists of this there. Let's see. But it's too early to say much about that one, other than that they built it well.
Thanks.
Great question.
Anyone else? Question for?
So Utah is a line state. We're a 1% marinated state. You come from Idaho, where you might get a line project every 3 or 4 years. There is a reality that lime is also helping with that stiffening. And so you may need to make some choices related to what you're doing. Now, something that Howard is now starting to talk publicly, that we've been talking for a couple of years, they've been doing TSRs on this with and without lime. And at that level of binder coating, your TSRs are fine. There becomes an increasing question of, are we really needing and, to put in some sort of anti-strip. I didn't mention it, but all but one of those 43 projects have used a, what is also a liquid anti-strip, but it's also a warm mix technology. The one project that didn't meet density was the only project that didn't have that additive in. So their contractors from the get-go started buying that almost by and large. Now it's a standard part of their operation. Follow that. You should see it because, and you guys are using the Humber. I mean, if you're not seeing the stripping inflection point, and you probably won't. Now, there was a mix that one of your contractors sent to me that the software said had a stripping inflection point. So I just offer you a bit of a caution. You need to have a good person taking a look at the results of it, not just relying on the algorithm or software. It's probably improved now, but that software said there wasn't a stripping inflection point in that particular mix. And you could easily see that it was not true. It was a unique dip, you might call
Anyone else?
it. Right.
Thank you, Dave. Really enjoyed the presentation. Any recommendations for those of us that see this stuff from Utah, are awed and impressed by the numbers and the kind of jump in that you guys has taken? How do we attempt to bring those benefits to our agency where we don't have the same material, we don't have the same climate, we don't have mountains?
Right. So firstly, the benefits that they have because of the way they've embraced it, the way their contracting community has also embraced it. You have great synergy between those two organizations within the state. The suppliers of the binder out have also come on board very quickly. And the original project at Beck Street and then out to Wendover was about a 50% premium on the cost of that mix. But because of everything else, we're now dealing with what falls in line with ordinary economics, you might say. So first of all, I would say, don't expect that. You're gonna have to get that kind of embracing from all the different parties to see that price come back down into a more reasonable value. So you're gonna have enough tonnage, you're gonna have to have the contractors happy with it. Contractors in Utah love this. The other thing to pay close attention to is what binder is the right binder for us. Especially with the aggregates that we have, that also comes into play, but we build a good structure. 100% fresh material, no naturals allowed. And I think the no naturals allowed really gets some people concerned, but it's a key component to this system that we're doing. And so I might be willing to start trickling some naturals in after. I've got some projects on the ground, I've got good tonnage. I can tell you Howard isn't looking at changing that at all. What they are looking at is instead of 15%, maybe they're gonna jump to 20% draft and might creep that up some. But they're probably not gonna go too fast or too far on that either. And so it's really about engineering it for your location with your material. And that's what we're supposed to do. We're supposed to be engineers. And so this idea of let's just cut and paste what Howard's doing. If I was in Florida, quite frankly, I wouldn't be doing this, not like this. I would do it in a different way. With the imported rocks that I have from Nova Scotia or Georgia and the binders that I might need to build there. I would want it to work for my location, and we can do that.
What else?
Nobody do that, but, yeah, this is really exciting, excellent work, and it'd be great to see how it applies to other regions of the US and other states try it. What is like the storage stability or the binder supply side? So somebody's making this stuff up, because I've worked with highly modified binder before with fill for interlayers. We always kind of watch the weather and just make sure that we're gonna make this up. We're gonna be using it within a day or two or three. So, but that was very highly modified. This is starting to push that. So how long can you keep it if you get 3 days rain, 4 days rain?
Tremendous question. And quite frankly, when they first started doing this on those two projects, one of the projects, and it was the only one they struggled with, it was a storage stability issue because they tried to store it over the weekend. That was a system that was a little bit different, a little bit more modifier than what we're talking about now. The work that has been done with the suppliers they'll tell you we've solved it. And I've got unconfirmed, being told that there was one that sat for over 6 weeks in the tank. Yeah, you normally get that viscosity creep, I call it. I can't imagine that it lasted that long. but I know plenty of them that have been sitting for a week and are fine. Now, there's another thing that I didn't have time to mention, but since you asked the question, Bill, let me delve into it for a moment. All of the hot plants, there's 4 different suppliers, contractors that do this. All of them have switched to 4-inch lines. And they've gone to the heaviest Viking pump that they could find. The trucking community has also made a shift in their equipment to accommodate this more appropriately as well. And so that also is adding to the overall beauty in the state of Utah. And so, the problems that they had, in Bozeman with 4-inch lines would have been less pronounced. But with that binder, they still would have had some issues, and I don't think they would have had the storage stability, capabilities with that binder like they do in Utah. So it's all part of the chemical packages that they're putting together now.
Just following up on that maybe you can tell us, or maybe you can't, or maybe you don't know, how are suppliers, what are some of the things that they are able to do to get below that 3 Pascal/seconds in order to get the pumpability back? And obviously, great point. I mean, if plants are being retrofitted to make this type of mix, I think that is the right way to solve it, because other than that 3 Pascal/second doesn't really serve any other purpose. That's the only thing that you have.
100%, absolutely. And the only reason they did that shift is because of the tonnages that they're being asked to produce. So the ROI for the contractor to do that, and it's a chicken and egg thing that we were dealing with in Utah. How they're formulating, everybody's doing this. I know more than I'm supposed to, but I can't say much.
Anyone else? Actually, I have a question. Go ahead.
I will be leaving here in just a moment. I'll be back tomorrow morning. I've got a virtual presentation for Hawaii that I'll be giving in a while. And so just FYI, but yeah, please, Jim. Curt, what's your question?
So you mentioned about the cooling down problem. Has there been any or the new projects, anything always now with warm mix?
So it is a warm mix additive that they're putting in that. They're not running at warm mix temperatures. Typically 300 to about 320 is where they're mixing. That's another thing to keep in mind, and I didn't mention it. When you start cranking temperatures with the polymers, you speed up that viscosity creep. And so the normal process, if you're struggling at density, for example, what are you going to do? You're going to crank temperatures. That's the normal thing. You will struggle with what you produce when you do that. So you may not have trouble getting density, but you're introducing other problems that you're going to hate. You got to be careful with that. There are some attempts to try to bring that temperature down, but thus far, nobody's really been willing to be the first person to jump in that pool.
Okay, thank you.
No, there's one other thing too that's going to force this though. There's a new air quality requirement that the environmental agency for the state of Utah has implemented that only allows X numbers of tons of hot mix to be produced within a geographical area in a given construction season. And so in Salt Lake, they will hit that. And then if they're making this mix, their only choice for this mix or any other is to bring it down in temperature to meet that new requirement. So it may be by default that whoever the contractor is, that's the first one making a ton of mix after that threshold has been hit, is going to have to bring it down and see what happens. I know they're playing around with those lower temperature mixes and seeing what they can do in the event that they're the ones who have to actually prove it.
Okay, very good. Dave, thank you very much.
My pleasure.
For our third presentation this afternoon, Eshan is going to speak on balanced mix design. There, as you remember, in 2024, we go into pretty much the whole first day that balanced mix design, but there's been a lot of new and exciting things that have went on since then. So please welcome Eshan.
Thanks, Curt, and thank you, NRRA, for letting me be here and speak in front of you. You're hoping to see a lot of VMD results. You'll be disappointed. I don't have any results in this presentation. I'm just talking about the new structure of BMD that the BMD implementation working group is working towards a new AASHTO practice standard, and that's what I'll be presenting to you. But I have a great segue from Bill and Dave's presentation, lots of examples that you saw in both of those presentations apply to what I'm talking to you here. Also, everything I'm presenting here is really outcome of this organization or this voluntary group called BMD IWG, which is really a joint effort between NAPA and Federal Highways. That's really designed to help us move BMD forward, provide necessary tools to agencies to be able to start implementing BMD and really going through different tiers of implementation. Several of these slides come from Derek Nienerplan. So BMD Infrastructures is his new company. You probably know Derek. He worked for Maine DOT as a materials engineer several years, then worked with Federal Highways at Turner Fairbanks until last year, and now working as an independent consultant. He's doing tremendous amount of work within this implementation working group. So whatever I'm presenting here is not just my voice, but really things that are coming out of this group. If you want to know more about this organization or this group, you can scan the QR code. I have tons of QR code in this presentation. I think the presentations are available afterwards, so you have access to them. But if you are not member of BMD IWG but want to become, just scan the QR code. They have a link on the page in order to apply to become a friend. And that way you have access to all the meetings. It's again a voluntary organization. It's not like some kind of closed society or something like that. The whole objective of this group is to promote BMD, to provide tools, to use expertise that's around the world on this topic, and come up with really tools and products. So it's not a research organization. They don't support or they don't sponsor research. We do try to find avenues to do research on the topics that we think are necessary to continue to move forward on BMD. But the idea is really to develop tools and other type of outlets that agencies and manufacturers can use. So what is BMD? And as Curt mentioned, I know in this forum, we have talked a lot about BMD, so I don't think I need to spend much time on it. I did take language out of the current AASHTO PP 105, which is the current practice, provisional practice. That is what describes the approaches A, B, C, D that I think many people are familiar with, different approaches to do BMD. But the idea with BMD is simple, that we are trying to balance this performance space between our primary distresses that might be failing our roadways, whether it's rutting versus cracking. You may have some durability aspects in there as well. And I did copy one plot out of actually a MnDOT report that late Dave Newcomb did for MnDOT when they were first starting and looking at BMD. So this, I think many of you have seen plots like this. A challenge with plot like this is the only tool you have on this plot is your asphalt content, right? So where does high mod fit in? Because this is really inherently designed that we're just going to change binder content to find our optimal space. And that's one of the challenges that the IWG also recognized as we were looking at current AASHTO spec or AASHTO practice and thinking, do we need to reimagine the whole concept of BMD? Because A, B, C, D approaches are great, but they are really mixed design tools, right? They are really what you can apply, for example, how Bill applied it to look at these different sections with different type of modifiers. If you are an agency and you are trying to specify things, approaches don't really mesh so well with using that to specify a certain set of requirements. And then also they don't have a good enough way of directly fitting within a QA process that federal government requires you to have. Okay. So keeping those things in mind, and I'll just again refresh everyone's memory with 4 approaches that exist within the AASHTO world on BMD. You have A, B, C, D. is really taking your existing mix design methods and doing some kind of validation testing that I'll still do design the way I've always done for last 30 years. And then I'll run this test and make sure that it meets the threshold. Okay. B, again, the only tool in B is change your binder content. So now you do performance optimization by seeing what gives you your optimal binder content in context of that test. C, you still start with volumetrics, and then you can also adjust some of the components. Maybe use a different source of aggregate if you have some concerns there. Maybe you are able to use some of the additives or modifiers, things like that. And then D never realizes because D would require you to put full faith in the test and you don't even worry about what you're putting into your asphalt, right? So we have not really gotten to D on a routine cases anywhere in US. So that's what's in the current practice. IWG looking at this practice, seeing how do we go from design tools to actual specifying tools to QA process. Really thought we need to reimagine the concept of BMD because with ABCD, we have increasing levels of flexibility, but most states are stuck at A or stage before A, which is collecting data. We are not able to move forward, partly because there's a mismatch between how we design mixes versus what all may be required to fit within your QA processes. So while A through D conceptually makes sense, going from being most conservative in terms of just doing a check testing to least conservative and then having a more innovation potential, we have been mostly stuck in A and B, and that's not really opening up the box to use some of more innovative things like Utah's doing with their high model. Okay, and a good example there, again, most states that have moved to BMD, they still require 4% yield. So now we are still requiring that volumetric constraint, unlike what Utah DOT said, and then go to 1%, right? So three main things that IWG recognized. One, that the mixed practices are evolving. Our only tool is not just adding a little bit more binder to make it more crack resistant or take a little bit binder out to make it more rut resistant. We have to use things like plastics, rubbers, fibers, other type of systems, right? And A through D are good on a designer end to put mix together. How do we carry that information over to what we currently use for acceptance of mixes or project acceptance level or even mix approval level? And the third part is within BMD and approaches A through D, there's not really ability to have different levels for different type of distresses. So if I'm most concerned about moisture damage, but I'm a little bit concerned about cracking, how do I find something which is level A for one part, but C for something else? And that's where we thought of this new system, what we call a tier system, where you can have different tiers, where you can specify a mix which is tier 1 for cracking, but tier 3 for moisture damage. And it'll become a little bit clearer as I describe what those tiers are. So we did quite in-depth review of current BMD practices. That resulted in this document that you can get from the IWG website, and here's your QR code number 2 that allows you to download this document. But really what this document is saying is everything that I presented in these first 8 slides. Approaches are great. A lot of people are using it very well to design innovative mixtures. However, it's also limiting agencies' abilities to fully embark upon BMD and start to specify them and then continue on maturing them. So this document is a nice 2-page read that really summarizes all the challenges that we have with just the approaches idea and what are the priorities. How can we move more towards using BMD so that it can be easily specified by an agency. Okay? And it's really 3 main things. I won't go through all the other ones, but 3 main things. Start by looking at what current constituent and volumetric and performance requirements are, and that's what we call performance characteristics. Focus more and more on mechanical testing, right? That's the whole purpose of where BMD comes from, that we can start to put reliance into these mechanical tests. People call them oftentimes performance tests, tracking tests, rating tests, whatever you may have. Throughout this presentation, I call it mechanical testing because that's really what we are measuring, some kind of mechanical property. And then try to prioritize optimizing that performance, right? That's what we are after. If tracking is an issue, then we try to optimize on that side. And when we are putting more reliance on mechanical testing, we need to also provide some relaxation, as Utah did. So the objective here of the AASHTO practice, and it's not final yet. We are hoping that this summer AASHTO Conf will approve it and a new PP will be issued. But the idea with this AASHTO practice is to provide guidance on how to specify asphalt mixtures using BMD. It's not about developing a mix. We already have that PP 105, the 4 approaches. That's really good. That allows you to develop the mixes. It's not about how to evaluate mix either for acceptance. That's the next stage, but it's designed so that that next stage will fall in place once we have this goal. Just in terms of timeline, so this took about year to year and a half of effort to put it together with about 30 or so people really working on the idea, making sure that we had enough input. Also, there's an open period where everyone's comments, it was posted on IWG, sent to all the states that are members of AASHTO, which are all the states, for their address and comments. It was balloted last year in August. It passed with 1 negative vote, and I'll talk about that as well as comments that we have received. We have already addressed those, and we are hoping that this year it'll finally become a AASHTO practice. So summary of comments, most of them were editorial, so they were easy to address, just clarifying things, providing a good narrative of how it's different from approaches, why the tiered system, making sure that there's no confusion, there's not necessarily same thing as approaches. We are not repackaging the approaches and calling them tiers. The most significant comments, there's one more from Ohio that really wanted to ensure that approaches are kept, and there was some need for clarity. We worked with them, made sure that's clear in the current version. Federal Highways had really good input. They really wanted us to provide a good differentiation of how your constituent, your volumetric, your mechanical test requirements, what kind of standards, what are the differentiations there between having limits versus report only, and then Maine and several others subsequently also had good recommendations that put examples. Right? Examples are great because practice document, you have good summary of practice, but then if you put examples, that's where it must come home. So I want to actually show some of the examples that are in the current version of this AASHTO PP draft. So I've already mentioned this several times, but what's different? Different is approaches A through D. They are design methodologies. They tell you how mechanical tests can be integrated into a mixed design process. The tiers 1, 2, 3, they refer to the specification level of how BMD specification levels are set up, where 1 through 3 has the highest flexibility, most reliance on mechanical test. 1, maybe you're still new to this domain, you don't have established test or validated test thresholds, and that's where you start with full intent that you'll graduate to 3 eventually, right? So the idea is for every state to get to tier 3, starting from 1, and then moving up. A lot of states are already at maybe tier 2, those that have already had BMD for the last 6 or so years. So what's the process, how we followed, where we started? Started by just looking at what our current, if you take AASHTO M323, if you look at the current requirements for constituent materials, for volumetrics, and then those agencies that have BMD, what are their performance matrix that they have at present? And then start to shift focus towards mechanical testing to introduce flexibility, especially to the constituents and the volumetric sides. Optimize for these performance characteristics. I have a couple of slides talking about what are performance characteristics. And this is where also this approach, in my opinion, is more encompassing overall asphalt mix performance, not limiting it to saying we have cracking and rutting. Okay, so going more than that. Design it so that down the road we can incorporate it within QA processes and make sure that we are not leaving out innovative materials or application-based scenarios, such as there might be instances where you are mostly concerned about non-load associated cracking. You are not concerned about load-related cracking. You don't need to have performance characteristics associated with those, or maybe your state, you are not worried about moisture damage, so you don't need to worry about that. First part, pretty straightforward. I think this is the fourth time I'm saying it. Approach is how you design, tiers, how you specify. Tiers go beyond mix approval. So the idea is that with this, we'll be able to carry over and go into verification and acceptance during production. Knowing that BMD is not just tweaking binder content, we have other things that we can consider as well. We are not dropping or not saying that constituent and volumetric properties should not be recorded, right? They are great process control tools. Your binder content, your certain gradation limits, they really help you with your process control, and they could still continue to be part of your QC requirements. So they should still stay as a report only, because that will still allow you to look at your variabilities. But the tiered framework is also designed so that states can move at their own pace and then continue to move through those 1, 2, and third tier levels. All right, so performance characteristics. Here in this practice, we have 5. So again, rutting, pretty straightforward. Cracking, lot of language in the PP105 is just cracking as cracking. Here we have broken it into load related and non-load related. You don't have to have all of these performance characteristics in your spec. If you know what are your concerns, you can go with that. If you know that you are using it mostly for lower volume roadways where thermal cracking is primarily your concern, you can only have non-load related. But then within the same state, you have more of a high traffic volume designs, then you can also have load related be part there as well. We did add moisture damage as its own performance characteristic and also surface characteristics. A lot of agencies have requirements associated with friction, with polishing, and so that becomes a performance characteristic itself. And then, as I mentioned, there are 3 tiers. I'll talk about tiers in a little bit. I just want to talk a little bit more about performance characteristics. So for each performance characteristics, there's really 3 things that we are looking at. What are your constituent requirements? What are your volumetric requirements? And what are mechanical properties, right? And as part of the practice, within the examples, we provide a starting list of all the existing AASHTO and ASTM standards that exist, or even state standards. So there are several standards where they are just state standards. They are not AASHTO or ASTM like Texas Overlay Tester. You just have the TxDOT standard. So we provide that in the appendices so that you have a starting list. It's not inclusive or exclusive as in that you can only use that. It's just an example provided as appendix to the spec. And if you look at one example of such table for rutting, again, this IWG came up with it. It was open to public review, providing feedback on it. So there's just a starting list where if you look at rutting, what are your constituent properties, right? So obviously angularity plays a big role in it. We have that. Some states use Los Angeles separation just for the coarse fraction. There might be a microdewal for fine fraction. There's the fine aggregate, and there might even be the uncompacted void contents. So those are some of the things that rutting and aggregate constituent properties you have. On binder side, obviously your IPG, your MSCR, There might be additional requirements like percent recovery, as you saw in Dave's presentation. So all of those would go into the binder properties. Volumetric wise, you need to know your number of gyrations or compaction level. And then you have your volumetric properties that are in 323, right? And that includes everything from airwork, DMA, dust proportion, and so on. Mechanical side, we just provided a starting list here of all the different tests that are currently available and have been used by different agencies and researchers to study rutting, and that list is in there. But this is what we call performance characteristics. So when I say performance characteristics, what I mean is for rutting, there are certain constituent properties, certain volumetric properties, and some mechanical properties. Not all of these, so the state would choose one, right? And that's what will dictate what kind of rutting performance you get, right? Because this is what is going to control how your mix is going to rut. With tiers now is essentially how much flexibility can we do on first two by adding a requirement in three. Okay, that's all tiers mean. And the idea is tier one, starting step, maybe you can relax at least one or more, hopefully, volumetric properties by adding a mechanical requirement, right? So you saw that in high mod example, they relaxed the air void requirements. They still require VMA, but air void's now relaxed and is lower, and they require Hamburg as a way to bring the mechanical. With tier two, we are going more, so now you are relaxing at least two requirements on constitutive and constituent and volumetric side, and then adding one or more mechanical, so you are having at least three changes to how you are doing it right now. And then with three, as maximum reliance on mechanical testing, you are probably only retaining two of the performance tests. Okay? So the idea is that hopefully we'll get to a point in so many years where we are in tier three. But what drives these tiers is essentially how much field validation you have done, right? Because you have to have that confidence. You need to know that this is my ideal RT number with which in field I've had really good rutting performance. And that's really the journey that we expect states to go through. Same information shown in slightly different way, where it's shown more of climbing the tiers mountain setup, where you are starting with tier one with minimal relaxation, can adjust at least one or more volumetric constituent properties, more than three, and then finally retain no more than two of those legacy properties and put faith into mechanical testing. So here's again an example on rutting. We put this in the appendix of the spec, the current draft of the spec, where you have tier one, where you can add a mechanical test, and maybe instead of 4%, you can relax that air void requirement to be 2 to 4. The rest of it stays as is. Tier two, you still require, let's say if it's Hamburg like Utah does, we require Hamburg. We do waive air void to be not at 4, but make it 2 to 4, but also reduce or remove some of your angularity requirements on it. Okay, rest stays same. And then tier three, this is where you have shown that Hamburg works and you had great performance and you use these mixes through tier one and two. Now you can only retain maybe the toughness of your aggregate, and then the binder high grade and everything else is dropped off, and you have moved, finally graduated to relying the mechanical testing for doing it. Same information, slightly different format, but what I want to convey here is for your performance characteristics, and keep in mind tracking is again two, load associated, load related, non-load related. One nice thing about this structure is it allows you to use a mix of tiers, where you may be in a situation where you say, okay, we know that tipping inflection point works for us for moisture. It has been shown that in terms of studies that demonstrated. So we are already at tier three when it comes to moisture damage. Tracking, we are still looking at comparing tests. Rutting wise, we are maybe at tier two. We've had some validation, some early results. And then surface characteristics, maybe we are at tier 1. And this structure allows you to do it. You can have different tiers for different performance characteristics. And I'll just choose one example that we again have as an example in the draft that shows that what if I'm on tier 1 for cracking, but tier 2 for rutting, what does my net result look like? And the net result is essentially taking the requirements and putting them together. Okay, so cracking, you have mechanical test with the requirement, allowable range, let's say there's some flexibility with 3 to 5%, remainder is same. On rutting side, you have mechanical test corresponding to rutting. Allowable air range is even wider, and you are proposing to remove your max VFA, which is tied to the rutting potential. Your angularity requirements and remainder are same. So this becomes your final net. So again, the idea is let's look at what are our constituent properties, volumetric properties that really control these 5 performance matrix and just target. Okay. I don't think you need this slide in this room. Everyone knows the difference between what's mixed approval versus what's design verification and what's mixed acceptance. I do want to emphasize that the current AASHTO PP, while it's written and designed so that we'll be able to carry it into the QA process, it's not designed to cover the acceptance at this stage. It's mainly the domain that we're working on is the design approval and design verification. This piece, last piece, is being worked on, and hopefully we'll have a separate AASHTO document that focuses on the acceptance. So I'll just quickly go through the appendices of this current AASHTO practice or provisional practice draft that IWG has put together. And again, it's in my opinion, I'm a big proponent of problem-based learning. Actually, that's how I started to teach all my classes. So you need to really show how to do it as an example rather than just spending so much time on theory. So the appendices are great because they really bring the concept together. One thing to keep in mind, the way the tables are set up is same language that AASHTO uses. So you have for any parameter, either you have a minimum requirement, right? Like we saw with this presentation, minimum ideal CT requirement, or you may have a range as we have with VMA, where it needs to be between a certain value, you may have max. Or there's also report only, and report only are also important because a lot of them can be used as a process control parameters. So I don't expect you guys to read this table, but the main thing I want to convey is the set of tables in the draft of the spec. If you need that spec, you can email me and I'll be happy to share it. It's not a public document, so as long as you're just interested in seeing it for your reference, you can find it. But what we have with those examples is we have example of tier 1, tier 2, and tier 3 with constituent properties, volumetric properties, mechanical requirements. Again, non-exhaustive list. There's just an example, so we just picked one test for each one of the 5 performance matrix that we have. So in this particular case, you are using Hamburg for your permanent deformation. You are using ideal CT for load-related, DCT for non-load related, and you are not really interested in looking as much at friction and moisture at this point in time in this example. But you can see that we left pretty much all the requirements that you currently have in M323 as is. Okay. Now, if someone was to go to a next level with tier 2, really what happens is you are adding or putting more reliance on mechanical tests, and many of the properties up here start to go from minimum or max to report only. So that's really the only change that you are seeing, and same thing with tier 3. So it's much easier to see in this color coded version. So if we go from tier 1 to 2 to 3, everything in constituent and volumetric starts to become more of a reporting only, and the requirements keep on getting more reliant on mechanical tests. And that's really the whole concept with this tiered approach or tiered design that we have. So what's next? hopefully COMP will approve with this, at their next meeting, and we'll have a provisional standard to go in 2026. IWG is ready to start to deploy, to communicate this. That's what I'm doing here. I did list NRRA as one of the groups where we can talk about this upcoming thing. We will continue to coordinate with other efforts like AIEI or Capri. I'll talk a little bit about those entities in coming slides. And then also start to produce more resources, both through NAPA as well as TRB, in order to update the current guidance documents. And now we are working on how to continue this into your next part of asphalt pavement construction process. That's your production and quality assurance. So again, you have the QR code on the IWG that will take you to the IWG page. Please enroll yourself as a friend, and that will get updates, communications, invite to all the meetings have a web component, so you can always connect to them, provide your feedback on some of the drafts that we are working on. Before I end, I also wanted to show you some of the other resources. And last year, at this meeting, Amy F. Martin made a very good comparison between what's the difference between NRRA and Capri and AIEI and different entities. So you'll see some of that in these next few slides, but I just want to make you aware of resources. So AIEI is a cooperative agreement that Federal Highway Administration has with University of Nevada, Reno. And again, it's primarily focused on education. So there's not really a research side. It's really taking existing research projects, research products, and putting together tech trees, putting together webinars, doing workshops. I know Dave has presented through AIEI on high mod as well. So there's a lot of resources on BMD, including the ones that show the value proposition of BMD, right? They identified projects and have demonstrated what is the benefit to agency and the industry by going to BMD. IWG, I've already told you about it. I want to emphasize 4 products that we have already developed. First one, understanding and managing factors affecting asphalt mixture performance. I have no contribution to this. This was completely driven by agency and industry, with really producers and agency coming together and saying, okay, what are the things that really matter when you are producing asphalt mixtures, when you look at these performance characteristics, right? Is it the moisture content? Is it the condition of your baghouses? So it's a very good document that really tells you what are the things that you should be managing in order to get good mixture performance during production. The next one is aging matters. I was part of developing this document together with Fanyan from NCAT, and it's really focusing on importance of laboratory aging, long-term, short-term aging on properties that you measure in lab when it comes to things like cracking. The guidance document, it's amazing. There's really your cheat sheet if you are a mix designer, right? They mentioned the struggle that they're having in some of the states with good mix, not having access to good mix designers. If you're a mix designer and you've been asked to do a design that meets certain BMD requirements, this really gives you in a nice tabular form what changes to make to your mix designs to help improve which performance characteristics, right? We have these 5 characteristics. What should I change? How should I change gradation? How should I change binder content? How should I change even things like production temperatures, and what impact that would get me on my final product? And then last but not least, this description of the tiered system, which is reimagining BMD and moving beyond the approaches. Approaches got us long ways from just classical super pave. We are hoping with tiered, it will help us that propel into taking approaches and actually specifying. Capri, that's again a pooled fund, and a lot of work done through Capri on BMD side. They have excellent tools. If you are a state agency that wants to do the validation of a certain mechanical test and know what thresholds you should be using, they have developed a very detailed guide using case studies to show how to do it. Okay, so there's a lot of help out there to embark on this PMD journey and succeed at it. So that's the presentation. Again, I'd like to thank Derek and Andy Hatch for providing a lot of content for these slides, and I'd be happy to answer any questions from all.
Any questions for Eshan?
No data, no questions.
First time to have a really good look at this. Great presentation, great work with the group and everything you've done too, Eshan. So
Thank you.
I'm from a state where the contractors want to make good quality asphalt. They do, but they want to minimize the amount of testing. And so when I look at this framework, you might get a benefit from unconstrained and mixed design, which could put you in a new performance space, which might get you better performance because you took the conflicting specifications way and you've got, imagination from wow, you're just in a new place and that could be better performance at a lower price point, some materials that you can use. But I don't, and that could lower the cost, but I don't think you're lowering the amount of testing here. It looks like if you're reporting all these things, then you're running all these things. And eventually, if you're doing an unconstrained design and you trust the mixed performance tests,
Yeah.
you might be able to put away some of these
Yep.
tests and then not have to buy it, certify it,
Yep.
robin it, run it.
Yep. No, that's excellent point. And keep in mind that those are not on production and that report only is also the starting step, right? Until you are, so first of all, everything that's report only on this list is not even currently tested as part of the standard QA process. This is just to giving agencies, let's call it compromise as a way to see or get a feel for how the mixes are changed. What we are not saying, or what I hope it's clear, what we are saying is that's wherever you see report only is again, what we as IWG is saying is where you can start and then go from there. Because the idea is absolutely to not add any more testing effort, actually, if anything, reduce it, where if you go to, let's say, tier 3 on, I don't know if I have my written example here again. Yeah, if you go to tier 3, you are really not going to have any of the additional requirements besides mechanical testing. And then the two that you see there with just wrong slide. Bear with me. There we go. With just having the high PG and the LA abrasion, and that is what will become in future. That's all you are running. You are not really running what I showed initially as report only. Maybe it's confusing the way I presented it, but start by having those to be reported until you are comfortable. I know if that makes sense. Yeah.
Can you go back to 20?
Yeah. $24.
So, hey,
Table, yeah. With the 3 tiers.
maybe one more.
There,
Okay.
yeah.
So when you combine
Yeah.
tiers with different performance
Yep.
characteristics, it's not as simple as just taking the least common denominator, which is the most possible test.
Yeah.
Because I was looking at this, I'm
Yeah.
like, well, if you have reduced volumetrics in tier 2
Yeah.
for one test, but you still
Yeah.
have to do them for the other test, don't you just still have to do them?
So that's where we have to do it case by case. And what Derek's actually done is he's already done it for 4 agencies to show what it would look like. But the idea is look at what performance metric was originally put in for which requirement, right? So if we know that, okay, VMA, we are primarily trying to get sufficient amount of effective binder in the mix. Does it matter? Does it impact rutting? Does it impact non-load related cracking? Does it impact load related cracking? And go from there. So it's you are 100% right that it's not as simple as just taking the minimum requirements with each tier and then adding them together.
But that's where you require you to, and again, IWG would be very happy if you are a state and you want us to put your current specs through this to show what it could look like, we'd be happy to do it.
Seems like the target audience for this is really the designers.
Yep.
Or the architects of the BMD, which would be like the bituminous section in the state or an agency. Contractors would probably look at this, probably understand it, like some of it, not like some of it, but they just want you to make a decision and just show me the spec and we'll, work with you there.
Yeah.
This seems like it's when you're just trying to develop that BMD and then evolve the BMD, it's the people in charge of the specs.
That's 100% correct, yeah.
Very good.
Thank you. Joe has a question.
Read this correctly, struggle line, DOD is, it's not consideration of structural issues, and it's so we will fix. See that. One listening to this. It's not. No. What is part of the payment that's going to be like, that's huge. And it's a total reconstruction. Has interaction with pain. Was I just get into the theme that stuff is kind of this license that is being sent. And how do you factor that all into?
Very good question, Joe. So first and foremost, that's one of the big reasons to also break cracking into load-related and non-load related aspects. Second, nowhere here it says that you have one threshold and one test for whether it's a brand new box construction, whether it's mill and overlay, whether it's just asphalt lifts on full depth reclamation. And you are 100% right. You probably need different thresholds, maybe even different tests based on the treatment. And I think that we see that already with the approaches also, right? Where if a mix is going on overlay, oftentimes the requirements and the tests are different than if it's a brand new construction. So I 100% agree with you that there's no such thing as saying that I have a single mechanical test and thresholds that will work for all my different cases within my system. It'll have to be different because demands are different. You saw reflective cracking. It's not going to be the same case as what Dave showed with their construction 6-inch lift on what he called a granular base as strong as stone, right? That very different demand requirements. Yes, Phil.
Just going to add, I'm glad you mentioned the CAPRI work that they're doing. All this is dependent upon that we can make samples that are representative.
Yep.
I think most know that we can do it volumetrically. That took, I remember right after the launch of the SuperPay program, right? It took us 10 years to figure out I say we, when I left Kentucky and went to Dakota. But it took us 10 years to just figure out the angle thing that was going on, and we could all make the same sample. Few states are out there that still use Marshall, and they're struggling now to relate to the rest of the folks. Level 1, level 2, level 3 were all big words that we talked about in SuperPay, and we couldn't get them in. Could you imagine if we tried to actually have launched all the performance testing? We tried, right? Way back then, and one lab could do it, another lab could do it, but nationally it was just not going to work. And here we are 30 years later, and now we're finally getting it going. It's great. Now we've got to figure out how we can all make the sample uniformly and make it load at the same temperature, same aging, and get the air out of these things so that all the things you presented can work. So Capri is so much of that, and I just appreciate the it's working through all that.
Thanks.
Any other questions? I've got one.
Yes, correct.
Sean. So how do you, where does RAP play a part? Is that like a constituent or a source thing, like RAP?
Wrap,
Yeah.
great question. So I think we've, at least a third of the hours burned by IWG has been discussing RAP. Because RAP is such a challenging aspect when you think about where does it fit? Does it fit within constituents? And the general consensus is that it doesn't, because there's no such thing as a RAP. Right? Every RAP source will be different. And the idea is that we are going to, at least as a starting point, it's recommended that agencies are starting as tier 1. They are using RAP as a constituent, because again, even in tier 1, for your primary performance characteristic, there's still a mechanical test to catch your performance differentials.
Thank you. Okay, very good presentation, Sean. Thank you.